In single variable calculus, we were able to think of integration as area under a curve. Our goal with this chapter is to increase the number of dimensions and think of integration as volume under a surface. But before we can do that, we need to do a review of the ideas we used in single variable calculus. Suppose we have a function y equals f of x, and that we are interested in the area under the curve between x equals a and x equals b. The way we did this was by approximating the area with rectangles. We're going to start from scratch and build out all the pieces of this construction. Let's suppose that we are going to use n rectangles, and we're going to make them all the same width for simplicity. To do this, we divided the interval from a to b into n pieces so that each piece has width delta x, which is equal to b minus a over n. This collection of points along the x-axis is called a partition of the interval from a to b. We can then use these points to construct vertical lines that form the heights of the approximating rectangles. But what is the height that we're going to use? We have many choices. We can pick the height to be the value of the function at the right endpoints. We can pick the height of the function to be the value at the left endpoints. We can pick the height to be the value at the midpoint. Or we can even pick arbitrary points for each interval. Each choice gives us a different collection of rectangles to approximate the area. We will generically call these points x sub I star, where I counts the rectangles from left to right. Regardless of how we choose these points, we can write down the approximate area under the curve by adding up all the rectangles. Each rectangle has width delta x and height f of x sub I star. And then we add these together to get a result known as a Riemann sum. To get from the Riemann sum to the integral, we take the limit as n goes to infinity. We're going to repeat this process, except with an extra dimension. We're going to imagine the function z equals f of xy that sits above the xy plane, and we're interested in the volume of the surface that sits above a rectangle. The rectangle is the generalization of the interval. Let's focus on the rectangle first. In the x direction, the rectangle goes from a to b, and in the y direction, it goes from c to d. In order for us to make a partition, we need to decide on the number of pieces we want to make in both directions. We'll use m in the x direction and n for the y direction. This makes a total of m times n subrectangles. This also means that the length in the x direction is delta x equals b minus a over m, and the length in the y direction is delta y equals d minus c over n. We can also see that the area of each rectangle is delta a, which is equal to delta x times delta y. Above each of these subrectangles, there's a surface. If we extend this up into 3 dimensions, we get a box. The height of the box depends on the point in the region you want to use. Some common choices are the corners and the midpoint. Whatever point is chosen, we will denote it as x sub ij star, y sub ij star. The ij pair gives us the location of the specific rectangle. Once we've picked these points, we can then calculate the volume of the boxes and add them up. This gives us a double sum called a double Riemann sum. This is what we use to approximate the volume under the surface. From here, if you're given a specific function and a specific rectangle, you can actually plug in values to get a numeric result. Activity 11.1.2 walks you through that, so I'll leave that one there. The book formalizes this process into a definition. It's a bit long and wordy, so I'm not going to read it off word for word, but here's the summary. Let f be a continuous function on a rectangle R. To get the double Riemann sum of f over R, you partition the rectangle into m pieces in the x direction and n pieces in the y direction to get m times n subrectangles. Inside of each rectangle, you pick a point that will be used to calculate the height of the box corresponding to that rectangle. Then you calculate the volumes and add them together, and that result is the double Riemann sum. Just as with single variable calculus, as the number of pieces in the partitions increases, your approximation gets better and better. The double integral is the limit of the Riemann sums as m and n go to infinity. And that's formalized in the next definition. Definition: let R be a rectangular region in the xy plane, and f a continuous function over R. With terms defined as in the double Riemann sum, the double integral of f over R is the limit of the Riemann sums as both m and n go to infinity. There's a bit of a notational hiccup here. I will always explicitly write the double integral sign for a double integral. However, some people will use a single integral sign and implicitly use the dA term and the region of integration to indicate that it's a double integral. I think that's a confusing way to do things, but some of the online homework problems in the book might do that. Hopefully you'll be able to understand based on the context. Looking back at single variable calculus, one of the first issues we ran into with area under a curve is the fact that sometimes the function is negative. You might recall that we treat those areas as being negative values, so that we're actually talking about a signed area. The same thing extends to volumes. If the function goes negative, then we treat the volumes as being negative, which gives us a signed volume. So the double integral can tell us the signed volume of a region. The idea of area under a curve also leads us to the average value of a function. The concept is easiest to visualize in single variable calculus. After we've calculated the area under the curve, we can imagine redistributing the area across the whole interval and converting that area into a rectangle. The height of this rectangle is what we call the average value of the function, and we can write down the formula for it using an integral. The same thing works for double integrals, except that it's now a volume that we're averaging out into a box, instead of an area that we're averaging out into a rectangle. But it's really the exact same idea. Notice that the length of the interval has been replaced by the area of the region of integration. This is the natural generalization of the size of the underlying domain when we move from one dimension to two dimensions. There are a couple properties of double integrals that mirror the properties of single integrals. The integral of a sum is the sum of the integrals. We can also factor out constants from an integral. And integration respects inequalities, and by that we mean that if f is larger than g, then the integral of f will be larger than the integral of g. This section is mostly a review of the concepts that go into integration. On the one hand, it's new because it's a multivariable function. On the other hand, these ideas are the same ideas as in single variable calculus. In the next section, we're going to see how we can apply our previous integration knowledge to the double integrals we just created.